Hi, welcome back to the next installment. Now what happens is, if you know me, you know that I don't like all this guessing and substituting kind of thing. It's always irritating because you have to make a lot of guesses. So is there a clean way of making sure of two things? First, I don't want to find higher order polynomials and go on substituting into Airy's stress function and trying to see if it is 0 or not. I mean, this del squared, del fourth. I mean, you know what I mean, right? So I don't want to do that. At the same time, I want to be able to calculate displacements and things like that, and I don't want to keep integrating over and over again. It's a headache. Is there a beautiful way to do all of this? The answer is absolutely yes. There's an absolutely brilliant way to satisfy del fourth A equal to 0 in 2 dimensions without even thinking about it, and that has to do with complex variables. Okay, complex variable, again, it's one of those things where people always have difficulty. So I want to give you a very quick idea of what the heck a complex variable is, and this, by calling it real and imaginary and all of this stuff, so it's always a headache. So I'm going to talk about it in a very quick way. That is, I'm not really going to do all the details, but I am going to talk about what the heck a complex variable is in a simple way. So, idea is the following. If you have instead of a real line, I have the real plane, that is the plane of real numbers. So this is positive numbers means to the right, negative numbers means to the left, I numbers means up, down. I mean, that's all. So if you want to say a point here, I'm going to write x plus 3iy. I mean, that's all. There's nothing to it. Okay. The fact that the square root of minus 1 is I comes from the fact that you can think about square roots in a variety of ways, and one of the ways is to how much do you have to rotate it, something like that. And if you want, I'll talk about it later. I don't want to talk about it in this lecture. Okay. So the basic idea is it's actually I don't know why this suddenly showed up. So the basic idea is actually fairly simple. So you can write it as x plus y iy. Also, if you vaguely remember, because x equal to r cos theta in polar coordinates plus I r sin theta, you can rewrite this as r times cos theta plus I sin theta, which is equal to r e to the I theta. Okay, and this is a really remarkable thing, and you can make your life a lot easier. So the nice thing about complex variables is not only can you do all these problems in Cartesian coordinates, you can do these problems in any coordinate system, any orthogonal coordinate system, polar coordinates, elliptical coordinates, bifocal coordinates. You can do all kinds of things. It's actually quite nice. Okay, so how does complex numbers play a role? This is where the beauty of our approach comes. The idea is, just like an ordinary function, you can talk about complex functions. So if you just say, okay, what is so if you just think of f of x equal to x squared, you can try f of z equal to z squared or cos z or whatever. So f of z squared is x plus iy squared, and you know how to do it. It's x squared minus y squared plus 2ixy. So the nice thing is, if you take any complex function, it has a real part and an imaginary part, and you can actually get all of these things. The original real function comes out as x of f of x comma 0. That is, I can just put y equal to 0 and I'll get the real part of it. You can also do this in polar coordinates. For example, z squared in polar coordinates looks like r squared e to the 2i theta, which is r squared cos 2 theta plus I times r squared sin 2 theta. What's there? I mean, there's nothing to it, no? You can also do things that are really quite interesting. Cos z. So just like cos theta, you can take cos of a complex number. And you're thinking, what the heck is that? You expand it out and it will turn out to be cos x cos hyperbolic y minus sin x sin hyperbolic y. That's all. And because we are going to go on looking at real part, imaginary part type of things, we are going to write a nice short form which says FR is F real. So take the function, take its real part. Fi is F imaginary. That is, take the function, take its imaginary part. Okay. So now we come to the very amazing part. First thing is, if you take any complex function, f of z, which is reasonably nice, that means it has to be analytic. That is, it has to be written as a power series. Okay. If you take any complex function, the beauty is its real part and imaginary parts will automatically satisfy Laplace equation, del squared f equal to 0. If you want to generate solutions to Laplace equations, that's why I told you, when a mathematician sees a Laplace equation, they jump for joy, especially in 2D, because all it means is that pick any function that is a function of a complex variable and you can just do it. It's not a problem. Extremely easy. The beautiful thing is this result. Take two complex functions, f of z and g of z, multiply f of z by x minus iy and take the real part of it. It will satisfy biharmonic equation, del fourth a equal to 0. Can you believe that? Isn't that amazing? Just take any complex function. And the thing is, it works both ways. Any biharmonic equation, any biharmonic function will automatically can be written like this if the domain is nice. Okay, so all you need to do to generate a catalog is pick a catalog of f of z and g of z and go on generating. That's all. I mean, you don't even have to solve. I told you. Okay, now you can do a lot more than that. If you write an area stress function, you can actually calculate the displacements, and the result is given here. You can read that. I'm not really going to talk about this very much, but there, if you write your area stress function as a real part of x minus iy f of z plus g of z, then your displacement is given by the functions f and g. There you go. F real, f imaginary, and gradient of area stress function. That's all you need. You can calculate the actual displacements. I don't know why this keeps coming. Okay, that's all you need to know. Just create this area stress function. Boom, boom. You can get the displacement and you're done. There's nothing more to it. No? And not only that, you can calculate the stresses, everything. This one page is the critical thing. So what I would like you to do is just keep this page, because it tells you everything. It tells you how to calculate the displacement, tells you how to calculate the stress, tells you how to calculate the contour plot, tells you how to calculate the area stress function. All the starting point is f of z, this guy and that guy. If you have these two, area stress function you can compute, displacements you can compute, stresses you can compute, the stress flow, stream functions, the contour plots for the stress you can compute. That's all. Okay, that's the beauty.